Okay, good afternoon, everybody. A very warm welcome to you all. And again, we're delighted to bring you the first ordinary meeting of 2021 via webinar. So we're really pleased to have so many of you with us today. So I hope you can all hear me and see me okay. So first of all, before we begin in earnest, we just have some housekeeping to go through. So again, as normal, if you look at the top left of your screen, you should see a small green shield, and that symbol means that you're using the most up-to-date version of Zoom and that it is secure. I do also need to advise you that this meeting is being recorded. So questions can be asked at the end of the lecture that we're going to have this afternoon, but as you will be muted, please could you use the chat facility, which is found at the bottom of your screen, to ask your questions. And your questions should only come to the panelists, and then they will be read out by a member of the RES editorial team, Dr. Louise Alexander. So for the purpose of the Observatory magazine report, please, if you could write your name at the start of your question, if you're happy to be included in that, that would be really helpful. Okay. So I'm just pausing because there seems to be a few issues with video. My video is on, so I'm hoping that everyone can see okay. Okay, so first of all, just to go through some important deadlines. So at the moment, the nominations are open for the RES prizes for the best PhD theses in astronomy and geophysics submitted in 2020. So these are the prizes for the best theses in astronomy and geophysics, in astrophysics, the Michael Penston Prize, in solar system sciences and geophysics, the Keith Runcorn Prize, and in instrumentation science for astronomy and geophysics, the Patricia Tompkins Prize. The closing date for nominations for these awards, which carry a cash prize of £1,000 each, and the opportunity to make a presentation at a future ordinary meeting, is the 31st of January 2021. There's also an announcement for the deadline for the RES grants, and the deadline for the next grants round is February the 15th, 2021. Okay, so the next announcement is associated with the specialist discussion meetings for 2021-2022 session, so the next RES meeting session. And suggestions are invited from fellows who wish to propose specialist discussion meetings for the academic year beginning October 2021. Now, due to the current situation with COVID-19, you should be prepared to organise virtual meetings. So please see the website for further information, and the deadline for this is the 1st of March 2021. Okay, so the next thing to do, exciting announcement for this afternoon, is the announcement of the 2021 RES Awards. So I'm just going to share my screen. Okay, so I am very pleased to announce the recipients of the Society's Awards for 2021. The Honorary Fellowship for Geophysics goes to Professor Walter Mooney from the United States Geological Survey. The Honorary Fellowship for Geophysics goes to Professor Tamas Chelidze from Tbilisi State University. The James Dungy Lectureship goes to Dr. Karen Aplin from the University of Bristol. And the George Darwin Lectureship goes to Professor Filippo Fraternali from Kaptein Institute in Groningen University. The Harold Jeffreys Lectureship goes to Dr. San Kotar from the University of Cambridge. The Group Award for Astronomy goes to the Event Horizon Telescope team. The Winton Award for Geophysics goes to Dr. Julia Stavarts from Imperial College London. And the Winton Award for Astronomy goes to Dr. Cassandra Hall from the University of Georgia. The Fowler Award for Geophysics goes to Dr. Richard Morton from Northumbria University. And the Fowler Award for Astronomy goes to Dr. James Owen from Imperial College London. The Service Award for Geophysics goes to Professor Ian Crawford from Birkbeck College London. The Patrick Moore Medal goes to Miss Sarah Eames from Sandfield Close Primary School in Leicester. The Annie Maunder Medal goes to Professor Robert Walsh from the University of Central Lancashire. The Jackson Gwilt Medal goes to Dr. Floor van Leuven from the University of Cambridge. The Price Medal goes to Professor Emily Brodsky from the University of California, Santa Cruz. And the Chapman Medal goes to Professor Ineke de Mortel from the University of St Andrews. The Eddington Medal goes to Professor Heranya Paris from University College London. And the Herschel Medal goes to Professor Stephen Smart from Queen's University, Belfast. This year's Gold Medal for Geophysics goes to Professor Thorne Lay from the University of California, Santa Cruz. And this year's Gold Medal for Astronomy goes to Professor Dame Jocelyn Bell-Burnell from the University of Oxford. Many congratulations to all of this year's winners. Okay. So in today's meeting, we're going to now hear the James Dungy lecture for the 2020 awards winners. And this is going to be given by Professor Sarah Matthews from University College London. So Professor Sarah Matthews is an expert on the storage and release of energy in the solar atmosphere and has extensively studied the white light and related sunquakes in solar flares. Her discoveries have revealed insights into the dominant physical process involved and have shown that white light flares are not a mere consequence of so-called big flare syndrome. Sarah is an excellent and enthusiastic communicator of solar physics. I'm very much looking forward to hearing her lecture this afternoon. So I'm now going to hand over to Sarah. So hopefully she can share her slides with us and begin her lecture. So over to you, Sarah. Thank you very much.
Thanks, Emma. Congratulations to everybody who has received an award today. Some very, very well-deserved awards there indeed. I always cringe when people claim I'm an expert in anything. I'm not sure I'm an expert in anything at all, but I hope that I can at least give you some interesting things to think about this afternoon, and I thank you all for coming. So of course, science is never an individual endeavour. It is always collective, and it is always much better for having the input from as many people with as many diverse opinions and skills as possible. So I've listed at the bottom of this first screen some of the people who have been really instrumental in participating and in leading some of this work, and I have only contributed in a number of areas. It's completely inexhaustive, but it does, I hope, pick out the people who I work with most and have done most recently, and I apologise to anybody that I have missed out. So this presentation is going to be about solar flares, and it will focus on energy release and the more extreme end of energy transport. So I won't cover, in fact, too much on white light flares, except where they meet with sunquakes, but I will cover quite extensively the things that we know, or well, do we ever really know anything, but the things that we have started to learn about the energy release process. So let me first explain what this figure that you're looking at on this slide actually is. This is an early image from the Hinode mission from the EUV imaging spectrometer, the development of which was led by Len Culhane from MSSL in close collaboration with Louise Hara, who then took over the PI ship of the mission after launch, and with our colleagues in Japan and in the US at the Naval Research Laboratory. This is an image of the sun that you're probably not used to seeing. This is actually a flare, so let me use my cursor and show you that there are flare loops on the western limb of the sun. Here is the limb, and this is an image that is actually showing you what the width of a coronal spectral line, how it varies. So this is not intensity, this is a representation of underlying processes that lead to the broadening of spectral lines, and you can see that there are different colors here. So the yellow is where the largest line widths are, and the blue is where the smallest line widths are. And I'm going to come back to talking about line width quite a lot, so I thought this was a very apt image to start with. So I know that there are one or two solar physicists in the audience, so I probably don't need to convince them, or at least hopefully I don't need to convince them of why it is that it's interesting and important to study the sun. But for those of you who are not solar physicists, let me try to put in context why we're interested in solar physics and what we can learn from studying the sun and from studying solar flares in particular. So solar variability drives the variability in the near-Earth environment. So we have many good reasons to want to understand how changes in that variability will change that environment. Of course, it doesn't just affect the near-Earth environment, it drives variability throughout the heliosphere. And in fact, it controls the size of the heliosphere. So it's really an important aspect of understanding the solar system in general. That variability is, of course, driven by the evolution of the magnetic field on its many different scales. So that ranges from seconds to days and months and longer. And solar flares are one particular manifestation of that magnetic field evolution that particularly feed into changes in the near-Earth environment that we're concerned with in trying to understand the effects of space weather, as we talk about quite a lot these days. Even if we accept, and we should, that operational space weather forecasting is a very different proposition from fundamental research, we can only improve our ability to forecast space weather events and flares and coronal mass ejections if we understand the underlying physical processes that drive them and lead to their subsequent evolution. So there's always a benefit there. What the sun also offers us is the opportunity to probe energy release and transport in magnetized plasmas on an unprecedented scale. So the wavelength that we are able to sample, the emissions from the solar atmosphere with the coverage that we have there, and the spatial and the temporal resolution that we're able to achieve with current instrumentation, and even more so with instrumentation that has just come online and will come on hopefully line in the future, allows us to probe processes at intrinsic scales. So the sun really does offer us a laboratory for astrophysics. So what I've been playing repeatedly here over on the left are a couple of movies that show you, if I can get this to go back again, a famous, no, that one's not going to, but I stop that one, will it? The joy of PowerPoint. No, okay, well, we'll come back to this, but you saw here earlier on a solar flare happening here, and here you see the consequent effects moving out into the inner heliosphere. So you have a coronagraph image here showing you the expulsion of an associated coronal mass ejection and the subsequent particle acceleration, which we can observe as particle hits on the detector. So solar physics, as all of astrophysics really is about studying physical processes. And those processes include waves, instabilities, reconnection, turbulence, and probably most importantly of all, cross-scale coupling. So the processes that happen in the very small scale magnetic field are the ones that can subsequently lead to the really large scale destabilization that produces flares and coronal mass ejections and their release into the heliosphere. So understanding how that coupling works is a critical element of understanding solar physics. But what we also can use solar physics for, and if we come back to this idea of solar physics as a laboratory for astrophysics, what I'm showing you here is a series of images from a paper by Nadine Kalmoni looking at substorm onset in the Earth's magnetosphere and the analysis of auroral beads. And down here I show you an image from Graziella Branduardi di Raymond of the UV aurora in Jupiter's atmosphere. Next to some solar flare ribbons, which are evolving nicely as observed by the Swedish Solar Telescope. Now, there are many parallels between the observations and processes at the heart of all of these physical manifestations of energy release and transport. Of course, the parameter regimes are very different. We can't draw direct parallels, but what we can do is use the understanding that we have from each of these environments, in fact, but particularly from solar physics, to understand how these processes do differ in different parameter regimes and what those processes actually are. Okay, so moving on to solar flares. So most of our ideas about energy release and transport in solar flares are still framed within the context of what we call the CSHKP standard model for eruptive solar flares. So you see here a two-dimensional cartoon, which is adapted from a paper by Shibata in 1998, which shows you the underlying features of here. So the idea is that we have in this model the eruption of a filament or a flux rope. We have magnetic reconnection occurring in the corona below that, which leads to forces that help to propel the erupting flux rope and the associated coronal mass ejection out into the heliosphere, and also to produce heat, waves, turbulence, the acceleration of particles, and the production of new magnetic loops, which we observe as a solar flare down here in the atmosphere. So we see that those particles that are accelerated and trapped spiral down the field lines, and they produce emission in X-rays down here at the foot points. The heat that's produced as well during this process is just so enormous that it can't be radiated away efficiently. So we see the ablation of heated plasma, which we can observe and measure directly using spectral methods as Doppler shifts of spectral lines. And we see at the end of this erupting flux rope dimmings, so a depletion in the amount of plasma here, which maps very well with the expansion of the flux rope and CME as it leaves the atmosphere. I see that somebody had a raised hand there. I don't know if did somebody want to ask a question? I guess not. I will carry on in that case.
No, that's fine, they don't.
Okay, all right. So over here, I just wanted to show you some the really first observation that convinced even the die-hard skeptics of the existence and importance of magnetic reconnection operating in solar flares. So this is an observation that was made with SOHO, in fact, by Yokoyama-san. So things have moved on, but actually this two-dimensional model appears to be pretty good at accounting for many of the observed properties of solar flares, at least once the initial energy release has occurred. So to show you that we don't just work in 2 dimensions, here is a 3-dimensional cartoon based very much on that CSHK P model that I showed you in the previous slide. But what you start to see here with the 3D structure of this is the importance of the magnetic topology and the relationship between that magnetic topology, and in particular the details of the reconnection region with the sites of energy deposition. So in the 2D cartoon, what you saw were foot points at the end of a single loop. Here you see how those ribbons are formed, as we saw in the observations from the Swedish Solar Telescope. And you also begin to see just how much more extended this flare current sheet is, and how that also relates to the magnetic topology. I should play around with my trackpad there. Okay, so I've just told you that the standard model is a pretty good way of explaining quite a lot of the observations that we see. So what actually are the challenges and open questions that we need to answer? So I'm playing here a movie from a flare that occurred back in 2017. I'm going to refer to this a lot in different contexts as we move on, but I'll let you take in here just the beautiful erupting cavity, how it moves out, and the extended bright region behind it as it moves out into the heliosphere. So the main questions that we want to understand are, how is it that the magnetic field becomes unstable? Because that's the critical factor that's going to allow the energy that's stored to be released. Are there any unambiguous observational precursors that we can identify? So we might be interested in learning this in order to do better flare forecasting for space weather purposes, but actually if we want to study flares as well, then figuring out whether there are precursors that indicate the presence of particular processes that we know will definitely lead to a flare subsequently is an important thing to know. There's an ongoing debate in the community about the relative roles of instabilities and reconnection in that field destabilization and also the triggering of the energy release and also the timing. So almost certainly both of those are operating, but the relative timing of those is really important for us to be able to distinguish between different models. the duration of the ongoing energy release. So we typically classify solar flares as having what we call an impulsive phase, where most of the energy is produced in a very short time, on the order of minutes. But then we certainly see that emission carries on for longer than that. So can we understand that better? And then energy transport. So it's pretty clear that there's apparently more energy deposited in some locations than others, from the patchiness that we see in flare ribbons and the difference that we see at different wavelengths. So why is that? So let me start with precursors. So it's been known since the 1970s that soft X-ray and EUV line profiles are significantly broadened, and that often that broadening starts to occur prior to the onset of solar flares as we define it by this so-called impulsive phase, so the detectable signatures of particle acceleration. Often that broadening occurs tens of minutes or sometimes even longer before the impulsive phase starts. And we know from the observations that were made with the solar maximum mission in the 1980s that actually this broadening is independent of the longitude of the flare, while this process of ablation or evaporation in response to the deposition of heat in the lower atmosphere most certainly isn't independent of longitude. So that tells us that likely these flows are related to perhaps turbulence, or as Antonucci postulated in 1986, the flows that are generated by multiple different reconnection sites within the corona, which would also lead to turbulence. So what I'm showing you here are some observations from YOCO, from the Bragg crystal spectrometer, where we've looked at how that line broadening varies prior to flare onset. So you can see down here that you have a peak in the line broadening before the increase and peak in the intensity, and here we relate that to what we call non-thermal or hard X-ray signatures as well. So you see that this is elevated well in advance of the peak of what we call the impulsive phase. And you see that over here too. So if you focus down here, you can see that the line broadening has peaked several minutes in advance of the peak in the non-thermal emissions. I'm showing you here an image which is clearly spatially resolved. So back to the one at the beginning, just demonstrating that actually, we now clearly see how that line broadening varies even at the limb where we would expect the evaporation to signatures to disappear. But let me just finally move on and say that recent modelling appears to rule out the superposition of flows as the likely cause of this line broadening, which brings us back to this idea that really this does represent turbulence and the interesting possibility about how that relates to energy release. Okay, so this is spatially unresolved. So we can postulate that there might be multiple reconnection sites in the corona, but actually we can't really tell. So how can we make progress? So these were observations from YOCO back in the mid-90s. And until we had SOHO and later Hinode, we were stuck with great but spatially unresolved spectroscopy. So we had to find ways to try and figure out more about where this broadening was coming from and how it might be related to the energy release process. So in this work, what we did was to use the soft X-ray telescope also on YOCO, which allowed us to determine a temperature that could be compared with the temperature from the spectrometer, and then to identify using that where the highest locations of non-thermal broadening actually appeared within the flaring structure. So you can see that as the contours here. Why is that important? Well, because that really tells us what the origin of this broadening is in terms of the flare process. It doesn't give us the precise details of what of the actual process producing the line width itself, but it tells us how it might be related either to energy deposition or to energy release, depending on where it is within that magnetic field configuration. So the conclusion was that actually it is within and above the soft X-ray flare loops. So that's quite exciting, because that actually tells us that this signature that we're seeing early on before the energy release actually seems to be located in the region where we then do see the energy release. But of course, that was an indirect method of determining where the signatures were coming from. And it is always better to be able to do that directly. So here are some observations from some work that Louise Hara, Len Culhane, and some others along with I did back in 2013, looking again at this non-thermal broadening and its variation before flares begin. And you see three examples here. One is eruptive, one is non-eruptive, and the third one is eruptive again. And you can see some very different signatures in these plots, or these maps of non-thermal velocity, indicating where the first indications of an increase are with respect to the subsequent evolution of the flare. So what we found was that when the flare was non-eruptive, then these signatures were happening around the polarity inversion line. So that's where the magnetic field switches from positive to negative. But in the eruptive cases, the first indications of increases in non-thermal line broadening were actually at the foot points of the erupting structure. So at the foot points of this flux rope, where we then subsequently expect to see dimmings. And of course, I should say that I have skipped neatly over SOHO CDS, which was a fantastic instrument, which also produced spatially resolved spectroscopy, but just didn't fit quite so nicely with the story today. But I encourage you to look at those results too. Okay, so now we have an indication that actually, this non-thermal line broadening is really happening in discrete locations in advance of the onset of the energy release. And those locations appear to be related to whether or not the subsequent evolution of the flare will lead to an eruption or no eruption. So following on from that, this is some work that a student of ours did or led, and we collaborated with him on, looking at those similar signatures in the transition region and the chromosphere, so lower down in the atmosphere. So over here, you can actually see the coronal response in advance to this flare. So you see that there was, in this case, one small flare. The main flare happens over here. So you can see non-thermal velocity and intensity in this case tracking one another pretty well in the corona. But when you look in the transition region and in the chromosphere, so you have chromospheric signatures over here, we find that actually there's very substantial line broadening up to 40 minutes before flare onset, accompanied by actually very large Doppler flows as well, up to 200 kilometers per second. So interpreting that in the context of this cartoon here from Cheng et al., we see that this is consistent with the idea of at least some of the models for the building of magnetic flux ropes. So we have some quite exciting, I think, information about how line broadening can help us to understand the energy release, or the likely energy release process. But we're still very much interested in understanding this particular region here. So where the reconnection actually is taking place. So modeling reconnections are a pretty complex business. So there are models that reveal the existence of magnetic islands, accelerated particles, shocks, flows, turbulence. all sorts of things, and observations in the UV, EUV and X-ray enable us to see some of these kind of, or at least the indirect signatures of some of these processes. So I'm showing you again this movie with the 2D cartoon next to it, so that you can see that this is one of the clearest observations that we have of the region around this current sheet. So whilst we can't resolve the current sheet itself, we can see this heated region around it. And so this was actually the flare that the Hinode team had waited pretty much 11 years for, because this plot, this series of images up here shows you the Hinode ice observations of that plasma sheet and the line width. So you can see down here the intensity and up here the associated line width. And then I'm also showing you down here, for interest, the spectra associated with the cavity. So this element of the model here, and you can see some fantastically complex line profiles where we would normally expect to see a Gaussian, you know, indicating really the complex structure of the expansion of that cavity and the subsequent CME. But let me come back to this plasma sheet and highlight to you this simulation by Dorton et al., which shows the formation of magnetic islands within the current sheet. So these observations were interpreted in the first instance as signatures of turbulence that could be consistent with the existence of the tearing mode instability or plasmoid reconnection. The EUV observations can give us an indirect indication that, that they're consistent with that interpretation, but actually we can get some more information by trying to look at the unresolved structure using polarimetry. So this is some work by my current student Ryan French. So here you see the intensity of that plasma sheet and a cut through, and then you have the intensity from the coronal multi-channel polarimeter and the polarization signal. So what I want to highlight to you here is the correlation between the peak in the intensity and the drop in the polarization signature. This was taken a few hours after the flare started, and this series over here was taken actually the following day. So you see in this case no intensity signal, but you do see a drop in polarization still. So what does this mean? Well, there are two ways that you can destroy this polarization. One is through collisions, but density calculations indicated that the density was not high enough to allow that to be the cause of the decreased polarization. And so what Ryan did was to forward model the expected polarization signature for a number of different cases, as you can see here. And you can see that the one most consistent with the drop in polarization is actually one with unresolved plasmoids within that current sheet. And then if I remind you that actually this was still seen, although the drop in polarization was not as great the following day, it was still seen the following day, which indicates that there was still the presence even of this of these magnetic islands and continued reconnection more than 24 hours after the initial energy release. So I'm going to move very quickly from the energy release now to the energy deposition. So coming back to this idea that we have a kind of uneven distribution of energy deposition within flares. So sunquakes are probably the most extreme example of that. So these are localized and transient acoustic disturbances in the interior. So they were postulated to exist by Wolf back in 1973, and they're seen, as you can see in this movie here, from Kosvichev and Sharkova to propagate away from the flare site, and they accelerate as they do so because they're being refracted by a changing sound speed in the interior. But these really represent the most, I'm showing you a water wave down there for comparison. These are accelerating and so therefore different. So sunquakes really represent the most severe challenge, I think, to our understanding of how energy can be transported in this standard flare model. So if we accept that energy is released in the corona, then there are many, many scale heights that the energy has to travel through in order to generate a disturbance in the solar interior. So the question that I've been interested in answering with a number of different people over the last few years is how are these quakes generated? So the first ideas that were formulated by Kosovichev and Zarkova were around the generation of hydrodynamic shocks as a result of plasma heating, either by the direct precipitation of accelerated particles or subsequently ideas around pressure pulses that were generated by back warming, so by the massive amount of heat that's generated and transported down to the lower atmosphere during flares. A later idea by Hudson and Fisher was one around magnetic field changes, so the so-called McClymont jerk. This can also produce MHD shock waves as well as magnetoacoustic waves. So the question is really, can we use the observations in order to distinguish between these different ideas? And actually, do we need to? Is it the case that only one of these processes, or none of them, is operating, or actually are all of them operating? So on that last note, I'm showing you here some simulations from a paper from Conor McRae, who was a student of Sergei Zarkov and mine a few years ago, which combines the first flare radiative hydrodynamic model with a hydrodynamic model in the interior that generates an acoustic pulse. And so what this particular work showed was that actually there seemed to be almost all of these things occurring. But let me take a step back. So again, back to Hinode. And this is a particular case study. So one of the first ones that we did looking at the correlation with white light emission in flares. So you can see that here in a difference image as the grey. The black shows you where the sunquake sources are, and the other coloured contours are indicating where there is hard X-ray emission. So we were investigating whether or not particle precipitation and back warming could explain the sunquake driving in this case. And I think what you can see is that there is some good spatial correlation in some cases and not so good in others. Similarly for the temporal correlation. And then what I'm showing you here overlaid is another image from the X-ray telescope on Hinode, and this feature here represents a signature that we now know indicates that a flux rope is erupting, and here I'm showing you how the end of that erupting flux rope relates to one of the aggression sources, the sunquake sources over there. So let me take that a step further. So here is another flare, and what you see here are two sources, which are sunquakes at 6 millihertz. And you see those contours overplotted on the magnetic field, so the negative and the positive. And then you see those sources down here in relation to the rather patchy, as well as saturated in some places, ribbons seen in the chromosphere. And then up here you see those sources at the ends of a coronal flux rope. So what we found in this particular example is that there was very weak white light and hard X-ray emission associated with these sunquake sources. It was all associated with the subsequent flare loops that formed in the middle here, as indicated by this model linking back to that standard flare model. So this would be, I think, consistent with the idea of magnetic field restructuring as the driver for these sunquakes. But is that the end of the question? No, I don't think so. Obviously not. So some later ideas postulated by Alex Russell and his collaborators showed that you could actually drive sunquakes through Alfvén wave generation and Alfvén wave resonance, which then couples to the ponderomotive force. So given that we have plenty of white light flares that have no sunquakes, we have sunquakes where the white light emission is not always strongest at the location of the sunquake, and similarly for the hard X-ray. This work here looked to try and establish whether there was any observational evidence for the existence of Alfvén waves associated with sunquakes. So what you're seeing here, and I won't explain in too much detail, is actually a background image which shows you the blue wing of the iron 23 line at about 280 kilometers per second. But the contours in cyan and magenta are showing you where the sunquake sources are. And then down here you see a profile from the magnesium 2K line as observed by IRIS, which was substantially broadened to about 150 kilometers per second. And assuming that broadening can be attributed to Alfvén waves, we were able to calculate the associated energy density and establish that that was at least 2 orders of magnitude greater than the energy required to account for the acoustic power in the sunquake sources. So let me come back again to the idea of magnetic topology and the importance of that, both in terms of energy deposition in general, but in terms of specifically related to sunquakes. So sunquakes, even though we've managed now to identify 50 or so of them, remain the exception in association with flares rather than the rule. So that there are clearly a special set of circumstances that are needed for sunquakes to occur. So this particular piece of work was led by Lucy Green and Gerardo Valori, and we looked here at how the magnetic topology could really influence the channeling of energy in the flare down to the lower atmosphere. And the extrapolations of the magnetic field and the reconstruction of the magnetic field topology really indicated that in this particular case, there was a special set of circumstances that allowed the field to act as a lens to really focus the energy in the region where the sunquake was occurring. So clearly this is a fairly special field configuration, so perhaps that explains why it is that we don't see acoustic signatures associated with every flare. It's perhaps also consistent with the observations that we have of smaller spatial scales in ribbon structures. So we know as we move down in the atmosphere that actually the kind of locations and the area of the regions that emit in the lower atmosphere as a result of flares decreases. So I think it's fair to say that the jury is still very much out on what drives sunquakes, and there have been some recent papers at the end of last year looking at alternative ideas about what might be happening and trying to address some of the offsets that we see between some of the other types of emission. So I picked 2 extremes in some respect to talk to you about. One is about the really early onset of flares and how we can try to understand whether there are conditions that are more favourable to allow flares actually happen, and then how they might tell us about how the flares evolve, and then this very extreme idea of how do we get the energy all the way down into the solar interior. So I think it says that there are plenty of unanswered questions, not just in what I've talked about today, but in flare physics generally. And the standard flare model, unsurprisingly, has some fairly significant gaps. So there's much that we can learn from new data. So let me give a very quick plug for some of those new data sets. So here is first light from DKIST, and DKIST will also provide us with coronal magnetic field observations like COMP, but with 5 times better spatial resolution. But Hinode will also provide us with coronal magnetic fields. So down here you can see a magnetic field map of this active region over here using an EUV diagnostic, which opens up all sorts of possibilities for measuring the field on disk as well as above the limb, which is sadly what we are restricted to do with COMP and with DKIST, so very complementary. And then of course we have Solar Orbiter. Further in the future, I want to just quickly plug Solar C EUVST, which was selected by JAXA as the follow-on mission to Hinode for launch in 2026 or so, and was recently also, the NASA contribution was also approved for that just at the start of this year. So since we're running out of time and I have conscious I've overrun, let me just show you how much better resolution we will have with Hinode, and also we will have much more complete temperature coverage of the atmosphere spectroscopically, which will enable us to answer many of these questions much more effectively. And then finally, the European Solar Telescope, which would complement DKIST, providing multi-height chromospheric magnetic field information, which would really allow us actually to identify the presence of these alphane waves that might be propagating both down into the atmosphere but up into the atmosphere in a way that's currently impossible. So I'm going to leave you with this particular slide and try to convince you that solar physics is actually the original multi-messenger astronomy. So particularly focusing on this image down here about the internal dissipation processes in blazar jets, which, if you'll recall, are very similar to this idea of plasmoid reconnection and magnetic instabilities in solar flare current sheets. So thank you for your patience and attention.
Thank you, Sarah. You didn't overrun at all. That was absolutely perfect timing. So yeah, thank you so much for that fascinating lecture. Really wonderful. I've personally learned a lot. So I can see there are some questions coming through. So what I'm going to do now is just hand over to Louise, who's going to facilitate the Q&A for us. Thanks, Louise.
Right, okay, I'm going to start with Hugh Hudson, but I'm not sure if this is something that you then talked about later in your talk, Sarah. As you mentioned, the impulsive phase, where energy release is important, may last for a few minutes in a major flare. If we interpret this in MHD, the governing timescale might be the Alphen crossing time, which would be very much shorter. Do you have any view of how this may work?
So he's right. Of course, Hugh is always right about everything. Yes, it should be the Alfvén crossing time. I think the very steepest rise of the impulsive phase, where most of the energy release is happening, is substantially shorter than a few minutes. But this is one of those cases, I think, of how you define it, and maybe we don't have such a consistent way of defining this even after all of those years. There's clearly continued energy release happening in some of these flares for quite some time, and I think that's another aspect that really isn't completely consistent with that standard solar model, and something that we do need to understand further as we go forward and bring in modelling as well as observation.
Thank you. Francisco Diego would like to know, are flares always associated with sunspots?
Not always, no, but they are fairly infrequently associated with not sunspots, shall we say, active regions without sunspots. So certainly I vividly remember a spotless flare, which was also a white light flare from my PhD studies. In fact, it's funny how these things never leave you. But most of them are associated with sunspots, but no, we do get flares without sunspots some of the time, yes.
Eamon Scullion is asking, you mentioned EST First Light in 2027. Is that project now officially funded and going ahead? If not, what is the status of it?
In case Eamon probably knows the answer to the first part of that question. So the status of it is that we have EU funding to continue the preparatory phase until the end of this year. What we're doing at the moment is finalising the construction design for the telescope, and also working with national partners in order to secure funding to move to the construction phase in the end of 2 years. I mean, securing funding for these things is always a challenge. I think it's an even bigger challenge when you have to bring together multiple nations. So DKIST was, I guess, fortunate in that it only had to worry about the US in terms of funding. But so the status is that we are still moving forward. We are working to put together a legal framework and also a final construction design.
Stephen King would like to know, how do flare time scale models connect to current long-term sun magnetic field models? What causes flares? Do the flux ropes erupt from depth? How deep?
Okay, I'm not quite clear I understand the first part of the question, but in terms of what causes flares, then I think that's the question that we're trying to answer. So we know that it is the destabilization of the magnetic field, and actually there's been some recent work by some of our collaborators in Nagoya in Japan, identifying that actually some very small scale magnetic structures around the polarity inversion line can certainly appear to be reliable indicators of the beginning of a chain of events that will subsequently lead to a flare as we define it in current terms. But not all flares involve the eruption of flux ropes, and a significant open question within the community is when these flux ropes actually form. So there are some models where the flux rope is pre-existing, so it's formed by magnetic motions within the photosphere prior to the eruption, and there are some other models where the magnetic flux rope is formed as part of the eruption. So that's really what people are working to try to understand is how does that process work, and is those processes, and actually are they the same in all cases? And I think the answer to the latter is probably no.
And a question from Valerie Nakaryakov. It is found that very often during the impulsive phase, the non-thermal emission has quasi-periodic pulsations. We can consider these oscillations as a common and perhaps intrinsic feature of flares. A model of a solar flare cannot be considered as complete if it does not explain those quasi-periodic pulsations. Could you comment on this, please?
I agree. I think you're absolutely right. It's become clear that these do appear to be an intrinsic feature, and they may well be signatures of oscillatory reconnection. So I think this probably comes back. I mean, the standard model is a very simplistic one. It's a good framework for explaining some of the observations, but actually when you start to unpick all of the elements in that, they're hugely complex. So the process of magnetic reconnection is an entire field in itself. The study of waves, as Valeria is an expert in this area, it knows is also an entire field. So I agree that our flare models do need to be able to explain QPP, because they appear to be ubiquitous and fundamental.
Thank you. We've got time for one last question. This one's from Lindsay Fletcher. What fraction of a flare energy goes into the sunquake? What processes could affect that fraction?
So it's actually a relatively small fraction of the flare energy budget, as far as we actually know the flare energy budget, because there are significant gaps in our coverage of the spectrum, which mean that we don't know that particularly well. I think we, well, the calculations of the acoustic power associated with sunquakes have some fairly significant uncertainties associated with them, but certainly also the frequency at which the sunquake power manifests itself. So we can see that in some particular examples the power is all around 6 millihertz or so, but then in other examples that's much more. We see it at 7 millihertz and sometimes even at 10 millihertz. So one of the most recent papers on the topic is starting to look at this 10 millihertz emission. So I'm not sure that we have a very good handle either on the sunquake energy budget itself or the total flare energy budget, but it is actually still a relatively small fraction. I don't think there's any getting away from that.
Thank you. I'm afraid we don't have time for any more questions, so I'm going to pass back to Emma now. Thank you very much.
Thanks, Louise, for doing the Q&A, and thanks again, Sarah, for a fantastic talk. It was really very enjoyable. Thanks a lot.